Hi, my name is Anargeros, and this is my presentation on the Denavit Hartenberg formalism for the course of ECE 470, Introduction to Robotics. By the end of this video, you will be able to use the Denavit Hartenberg formalism to derive the forward kinematics map. By why would you want to do that? And the Denavit Hartenberg formalism is widely used throughout the world. In this course, we focus on the product of exponentials, but it's important to know both approaches in order to be familiar when encountered in different situations. Also, it is important to know it because it makes velocity kinematics easier and it standardizes the way to write forward kinematics. But how does the Denavit Hartenberg formalism work? So first of all, it's important to note that the Denavit Hartenberg provides a way to define the frames of the joints so that we can minimize the needed parameters to calculate the forward kinematics. For all links, we defined ZI axis to be aligned with the joint axis. This is the first step that we follow to define the frames for the joints. Assuming that ZI and ZI minus 1 do not intersect and are not parallel, we can define AI minus 1 to be the segment intersecting ZI minus 1 and ZI, and also this segment needs to be perpendicular to both these axes. After that, we define the origin of the frame I minus 1 to be the intersection of the previously defined segment and axis of ZI minus 1. Then we move on to define the axis XI minus 1 to be aligned with this segment, AI minus 1. Finally, we define the axis YI minus 1 using the right-hand rule. At this point, we finish defining the frame I minus 1. Following this procedure, we can define the rest of the joints using the previously defined frame each time. Having defined the frame for each joint, I minus 1 and I, we need only 4 parameters to obtain the translation matrix Ti minus 1. The parameters needed are the length of AI minus 1, which is called the link length. It is important to know that it is not exactly the same as the physical length in general. Also, we need to know the angle alpha I minus 1, which is the angle between ZI minus 1 and ZI around the axis XI minus 1, and it's called link twist. Then we need to define the distance DI between intersection of AI minus 1 and ZI and origin of frame I. This is called link offset. Lastly, we need to define the angle phi between xi minus 1 and ixi measured about the axis zi. This is called the joint angle. Moving on, we need to recall how to define TSI, which is equal to the product of TSI minus 1 and TI minus 1I. We have that Ti minus 1I is a product of 4 matrices, a rotation around x-axis with an angle alpha I minus 1, and translation about this axis with a distance AI minus 1, a translation about z with di, and the rotation about z using phi. It is important to know that these two x-axes refer to the I minus 1 frame, and these two axes refer to the I frame. The product is given in this form in the end. We can visualize Ti minus 1, comma I as the following sequence of steps. Firstly, we do a rotation of frame I minus 1 about its x-axis by an angle alpha I minus 1. Then we move on with a translation of the resulting frame along its x-axis by a distance AI minus 1. Following that, there is a translation of the resulting frame along its z-axis by a distance di. Finally, there's a rotation of the new frame about its z-axis by an angle phi. Previously, we assumed that the axes do not intersect or are not parallel, but what happens at these special cases? If the two axes of revolution intersect, then the segment AI minus 1 would be equal to 0. Then set xi minus 1 to be perpendicular as previously to both zi and zi minus 1. In this case, we have two possibilities for xi minus 1, and it is important to know that both are fine, but they result to opposite signs for the angle alpha I minus 1. In the case of the parallel axis, the choices for the segment AI minus 1 are infinite, but all of them have the same length and must be both perpendicular to zi and zi minus 1. We can choose any of these, but an important advice would be to choose it wisely in order to minimize the needed parameters, setting them to 0. But it's not necessary to do so. Until this point, we have talked only for rotational joints, but there are also prismatic joints. In order to define a prismatic joint, it's almost similar or the same as the revel joints. In this case, we choose the z direction to be along the positive direction of the translation. Then the link offset di is the joint variable and the joint angle phi is constant, which is opposite, if you think about it, to the situation of the revel joint. All the other steps remain the same as for the revel joints. Let's go ahead and see an example to understand it better. Here we see a mechanism with three joints, a rotational one, a translational one, and another translational one. Here we have already put in the frames, and let's see how we did it exactly. So remember, for a revel joint, we use the axis of rotation to define the z-axis of the joint, and for a prismatic joint, we use the positive direction of translation to define the z-axis of the frame for each joint. Let's see a specific example where we will try and figure the frame for the third joint. Here, we defined the z-axis for this joint to be along the positive translation. Then we have two possibilities for the x-axis since z and z1 and z2 intersect. We pick this direction for the x-axis, and then it is easy to define the y-axis, which would be defined this way using the right-hand rule. Finally, we need to define the matrix for the parameters of the Denavit Hartenberg. Starting from the first joint, we see that the segment AI should be 0 as we can understand, because there isn't any distance between the two z-axes, z0 and z1. Also, the angle between the axis is equal to 0 along the x-axis, since there is no angle between z0 and z1. The distance between the two is equal to d1, which is this distance, and it's equal to the distance between the origin of the frames. The joint variable, is defined as θ1, and you can see it here for the revel joint. If we move on to the second joint, we see that, again, the two axes have no distance in between them since they intersect. Following that, we can see that with respect to the x1 axis, there is an angle of 90 degrees between the two frames, which is with respect to x1 axis, it's a negative angle. Here, because we have a prismatic joint, the joint variable is d2, the distance of the translation. And then here we have a prismatic joint, so it is obvious that we have a constant angle phi and equal to 0. Moving to the last joint, it is easy to understand that again, the segment alpha, the segment AI will be 0, and the angle between the two axes is again 0, having a joint variable that is the translation d3, and a constant angle 0. This way, we filled up the 4 parameters for the 3 angles, and filling these metrics, we have concluded, after defining the frames, the Denavit Hartenberg formalism. Thank you for watching.